Hello and welcome to another video. In this video we're going to be working on minimum cost to make at least one valid path in a grid. And in this one you have an n by n grid, and each cell of the grid has a sign pointing to the next cell you should visit. And the sign is 1 if you are going right, 2 if you're going left, 3 if you're going up or down, and then 4 if you're going up. So basically this arrow is just represented by a number, and then here's where you're going. There could be some signs that point outside the grid, like this points outside the grid. And you're going to start at 0, 0, and you want to get over here. And they basically ask you, you can take any path you want, and you can also turn the arrow. So if you turn an arrow that has a cost of 1, and they basically ask you, like, what's the shortest path from here to here, given, or what's the minimum cost path from here to here, given you can turn these arrows. And I think they tell you can turn the arrows at most once. But you're never gonna, like in an optimal solution here, you're never gonna like revisit a cell. It wouldn't make sense. Like if you just think about that, like you're never gonna like get here and then go here and then like come back or something, because that's strictly gonna be worse. But essentially, yeah. So in this first solution, so the way you can go is you can go here, and you can come down here, and you can turn this arrow down. So that costs you 1. Also, actually, when you come here, you have to turn this arrow down. So turn this arrow down, turn this arrow down, turn this arrow down, and then you're where you need to be. So that's going to be cost 3, and that's going to be the best. If you follow, like, I guess maybe there's some other things you could do, but it's going to be worse, right? Like, let's say I turn this down, and now I also turn this down, and then I guess that's the same as well. So this is also another way to do it. Yeah, so either one of these is fine. But essentially, you can't do better than that. Okay, so in the second example, you don't need to turn anything, so you can literally just go here, this, like this, and then you're done. So this is 0. Third example, yeah, basically you're going to go here, and then you just want to turn this down. So that's going to be 1. So how do you do this, and like what do you want to look for? So the first thing is you look for constraints. So this is pretty easy constraints. This is 100 by 100, which means as long as you have something better than like m by n times n by n, like you can have a log factor here or just this will be fine. If this was 1,000 by 1,000, you'd basically like all the same stuff would work. Like you can have a log here and it would be fine. Yeah. So yeah, essentially how do we do this, and like what approach can we take, and like what algorithm do we take? So for shortest path, you're basically gonna always want to look at one of two things, either BFS or Dijkstra. And the way to figure out which one it is BFS is whenever the cost of going from one cell to the other is always like the same. Like 1 or something, or 0 or something, right? Because basically if you're asked, like, if I start here and I go here and the cost of going every cell to every cell is like 1, then I can use BFS, because essentially if something is in my queue first, it'll come out first, and then that's fine, and the cost of everything is the same. And then if the costs are different, then you want to use Dijkstra, because just because something is in your queue first doesn't mean it should come out first, right? Like maybe the cost from here to here is, you know, like let's say actually this comes into your heap. So in Dijkstra you use a heap. This would come into the heap first. Maybe this would come into the heap later. But then the cost of like this path or something is really small. The cost of this path is really big, and so on. So what can you use for this problem? I think Dijkstra makes more sense. So, but I'll kind of go over both, and there is a BFS solution. It's a little bit tricky, but you can kind of apply this to all your BFS problems for once. There's just basically one constraint, and I'll talk about that. So let's talk about Dijkstra first. So Dijkstra is pretty straightforward. Basically, all the time you're gonna have a heap, and then you're gonna have in your heap you're gonna have some values, and it's usually like the distance, and then like the XY coordinates or something. And essentially, what you do is you just plop from the heap the shortest distance, and then you from there you go everywhere you can. You add to the heap, and then eventually you get here, and you have like a visited set and stuff. And so how would we do that with this? So it's a pretty simple Dijkstra with a slight modification. Essentially, all we do is whenever we're at a cell, we can go to any cell we want, because we can turn this arrow. So from here, we can go here, we can go here, we can go here, we can go here. So there's kind of like 2 things we have to do. 1 you do normally, and then 1 you're going to add. So 1 can't go out of bounds or where we've been before. And that's just in a normal Dijkstra, like you're never going to want to like add out of bounds elements and things like that. But the new thing is we need to check, is square we go to, or actually if square we go to moves the arrow. And what I mean by that is, like, let's say we're here and we decide to go down. Remember, we're never going to revisit a cell, so we don't actually have to turn this arrow. We're never going to come back here again. You're never going to have an optimal solution that will revisit a cell. So, but we need to know, like, if we went from here to here, did this cost us anything? And because we're not going in the same direction as the arrow, we would have had to turn the arrow. So going from here to here costs us 1. Going from here to here costs us 0. So basically, whenever we make a move in Jigstra, we're just gonna say, like, are we moving the same way that it's moving? If yes, then we can just add the same distance, and on our new x and our new y, you know, call that like x1, x2 or something, whatever. And then you just keep doing this. Or if you had to change it, then you would just do distance plus 1, and then your new x and your new y. And then the rest of it is just cookie cutter Jigstra. So if you don't know Jigstra, just try like a basic Jigstra algorithm before doing this. So that's how you could do that with Jigstra. Basically just put in cells. Whenever you go to a new cell, just check, am I moving the same way as the arrow? And then the first cell that gives you this will give you the right answer. So you can actually do this with BFS as well. And the reason it works with BFS is, like I said, with Jigstra, if path lengths are different, you can use Jigstra. But here, path lengths are actually not, like, there's basically only 2. And in this case, you can also use a modified BFS. And so the 2 cases are distance stays the same, or distance increases by some constant number. And in this case, it always increases by 1, right? So in this case, it'll be 1. So we can actually use BFS. And the way we can do BFS is we can say whenever we pop out a cell, so we're going to have some Q, and whenever we pop out a cell, we're going to have the same exact logic as a normal BFS, but we're just going to check here, does our distance increase? And if our distance does increase, then we're going to put in the next node at the end of the queue. At end. And if it does not, then we're going to put the node in at the front. And basically what's going to happen there is, imagine you have some queue with some numbers, like let's just say we have some values here. Like maybe this has value 1, like let's just look at this as an example. So let's say our initial queue is here, and then every node will have, let's just do a couple of these examples essentially. Like let's say we start here and just like walk through some nodes. Actually, yeah, let's just do this for a couple nodes to kind of show how this will work. So basically, we're going to store 3 things for this. So let's make this a little bit bigger. We're going to store the distance and then the XY coordinates. So I actually want to make this smaller if I can. So distance will be 0, XY will be 0. So when we pop this cell, out of bounds is invalid. And we're going to forget the visited set for a little bit, or I'll just mark it crossed off. So whatever, we'll have this crossed off. So we can go here and here. And just to quickly, so this is like 0, 1, 2, 3. 0, 1, 2, 3. So if we go here, we have the same distance, which means that every single cell with the same distance should be visited before we increase the distance. So if we do have some valid path that takes a long time, like let's say this arrow was going down here, this was going down here, this is going down here. All of these would be visited before you're actually going to go here. Because if something has the same distance, like we popped our node, then we're going to put in all valid nodes that we can get to with the same distance. So we're going to put in this node over here. So we're going to put this node over here. So this is like row 0, column 1. And then we're going to put the other node we can go to at the back of the queue. So we don't have anything, so the queue will go here. Don't know why that happened. Interesting. Okay, so essentially, yeah, so here we're going to put in like 0, 1, or distance 0, and then the xy coordinate is going to be 0, 1. And then here we'll put in this coordinate here, and this is distance 1 with xy coordinate 1, 0. And then when we pop this guy, which is this cell here, so we're going to pop that, mark it. Now, same thing. We're going to put in the cells we can go to from here, which is this cell with the same distance. So we're going to put that in at the front again. So 0, 0, 2. And then we can also get to this cell, which is 1, 1 with a distance of 2. So you can see how basically, like, if we just keep taking the cell with the same distance and putting it at the front, we're going to visit everything with the same distance before taking the things that are bigger. So this is called like a thing like 0, 1 BFS or something. And essentially this only works, and you can only do this when you have these two cases where distance either stays the same or increases by some constant number. If this wasn't 1, if everything was like 5 or something, that would still be fine. But if they increase by different numbers, then you can't do this, and then you would have to use a heap. But in this case, you can use a 0, 1 BFS because our distance either stays the same or increases by 1, so we can just do this front-back thing. So let's take a look at the code. And it's a little bit annoying in Go. Queues and heaps are kind of annoying in Go, but not that bad. So essentially we get the rows and columns, we get the directions, we get a deck, which is a list in Go. Maybe there's other things you can do. So our initial value is the distance is just 0, and then xy coordinates are 0, 0. We have our visited. Then we essentially, while we have a deck, pop from the front, get everything. If we reach the cell, just return the distance. If we visited, continue. If not, we can mark it true, and then we can take a look at the neighbors. So we just basically add the directions to our old value to get our new cell. And then we have to check, like, are we in bounds? So if we're in bounds and we haven't visited, then check, does the distance change? So if we're going the same way we were going, and the way to do that, like I said, is basically just check, you know, like which direction are you going to with an index, and then which direction is in the cell. And I just made them all the same index. So essentially, I think in the problem they said, yeah, so 1 is right, 2 is left, and then down, up. So I did the same thing for my directions. So you have right, then left, then down, then up. So at index 0, this should be the same as the value in this grid -1. In here, this should be the same as the value in the grid -1, and so on, because this is 0, 1, 2, 3, and the values are 1, 2, 3, 4. So that's why you subtract 1 to get the same. So if it's the same, push to the front. If not, push to the back. And you add 1 if it's not the same. Then theoretically, you should never you should never return here. You should always get an answer, but good to sometimes when you're debugging, just have like a default value. That way, if you do get this value, then you know you'd like screwed up. So yeah, I think it's prettier to use this 0, 1 BFS. And I think using like Jigstras would be simpler, make more sense, but also I guess now that you know this thing exists, you can use this if you run into these problems where you have something where you have these conditions. Yeah, and as far as the runtime, and I could probably optimize it a little bit more, doing the same kind of stuff where if something's in my queue already, don't add it in. Actually, yeah, I don't know if you can do that here. So normally I add things to the visited set right when something's in the queue, but I don't think you can say like because it's in the queue it's going to get processed faster. Because imagine if I have something here, I might add that same thing in the front afterwards. So I think you can only add things to visited here when you actually process the number. But yeah, okay. So time, this is mn space mn for the visited set. So. And then, yeah, so hopefully this was helpful. If it was, please like the video and subscribe to the channel, and I will see you in the next one. Thanks for watching.